Hi, this is Group20, and we are presenting our group project on Costa Rican household poverty level prediction. Our group consists of 4 members, Wang, Jingtan, Yanli, Ray, and Xinyang. Let me introduce the problem. We have a dataset with data related to living conditions of a household or an individual. And we want to predict the poverty level ranging from 0 to 3 for each household. This is clearly a classification problem. We use the divide and conquer strategy to break the problem down into 4 parts. The 4 parts are data preprocessing, feature engineering, dimensionality reduction, and model building. Our presentation is also based on this breakdown. Other than that, in the end, we will present the results and our discussion. Now, I will pass on to Ray to talk about preprocessing.
Thanks, Xinyang. As the raw data provided contains missing values, outliers, and inconsistencies, thus, we need to preprocess the data to remove these abnormalities to achieve clean data. First, as you can see, the training set contains missing values in these 5 columns. For V2A1, which represents monthly rent payment, V18Q1, which represents number of tablets each household owns, and REZ, which represents years behind in school. After checking the data and competition discussion, we found out that the missing values for these columns simply mean that their values are 0. For example, for V2A1, missing values in this column represent that the household has no rent to pay. For mean education and SQB mean education, they mean average years of education for adults and the squared value. As dataset also contains similar features, we compute the values for these 2 columns using feature S-coloring, which means years of schooling. Dataset also contains outlier data. As you can see, the maximum value for REZ, ESC in the test set is 99. However, a person is not likely to have 99 years behind in school. After checking the competition discussion, we found out that this column is only valid for values between 1 and 5. Thus, we set any values larger than 5 back to 5. We could also notice the existence of inconsistent data, as both feature sanitary 1 and V14A represent the existence of the toilet. Their values are not mutually exclusive. Thus, we fix this by assuming that if there is water provision for that household, there is toilet. Otherwise, assume there is no toilet. After that, we plot the data to explore its distribution. First, we plot the distribution of the target class. As can be observed, there are far more households with non-valuable poverty levels than households with other poverty levels. Thus, we are facing a problem with the imbalanced target class distribution. This could indicate that we may face some problems in predicting households other than non-valuable poverty level, as we see far fewer data samples on them. We plotted all numerical features against the target poverty level to explore the data distribution. Due to the time limitations, we only take some interesting ones here. As can be seen from the above plots, for all the listed features, its numerical values differ in the distribution for households with different poverty levels, which indicates that they may play an important role in later classification. We plot the categorical data by plotting its one-hot encoded features against the target poverty level to explore the data distribution using both scatter plots and heat maps. Because of time constraints, we pick only one example to discuss here. This feature represents wall quality. E paired 1 equals to 1 if walls are bad, E paired 2 equals to 1 if walls are regular, E paired 3 equals to 1 if walls are good. As you can see, household with non-valuable poverty level tends to have good walls. However, the worse the poverty level, the more of them have regular or even bad walls. These differences indicate that this could be an important feature in making prediction. Then, I'll pass time to Xinyang to talk about the feature engineering process.
Thank you, Ray. Now it is my turn to introduce to you how we engineer the features to obtain better performance. We used a 5-step approach to feature engineering. The 5 steps are education processing, building new features, aggregate data, label encoding, and geographical features. We will introduce the steps one by one in the next slide. First, education processing. We have 3 input variables, 2 of which are Boolean, which means whether or not the male or female head has received education, and 1 integer, which means the years of education received by each individual. Our output is the years of education received by the head of household. To build new features, we used an exhaustive approach to create new features from numerical variables. Here is how we do it. We take all numerical variables and pair them such that the pairs cover every possible combination. And for each combination, we apply all possible arithmetic calculation. After obtaining the results, we manually separate the list of meaningless results from the list of meaningful results. After deleting the meaningless results, we get a list of new features, as is shown in the screenshot here. We have a second approach, which is called FE2, which means that instead of exhausting all the possibilities, we manually select the variable pairs that can have an indication on poverty level and select the method of calculation to it. In this way, we obtain a new list of features that is less than the number of features obtained in the previous method. Next, we do data aggregation. We want to aggregate all the data in a family to the head of a household. We select the variables to aggregate and select the aggregation methods suitable to each variable. Here's an example of the aggregated columns in the dataset. You can see that there is mean, there is sum, and there is maximum and minimum. Because the original categorical data are encoded using one-hot encoding, we transform them into label-encoded variables. After transformation, you can see the examples of the transformed data here. In the end, we create geographical features. We have received the region of each household in the dataset. We assume that regions can imply the poverty level. So we take these steps to create geographical features. First, group by region, and then calculate the means of numerical variables and one-hot encoded columns for each region, and at last append these calculated results. How do we interpret the means? The means of numerical values mean the average level of the variable in their region. For example, the mean of Hogger means the average number of children, adults, and old people in a household in a region. For one-hot encoded columns, things are a bit different. From the deduction on the screen, you can see that the means actually mean the percentage of households with value 1 for that column. Let us take an example of Ilimbasu. Let's say that the current row represents a household H1 which lives in region R1. Then the value of this column in this row represents the percentage of households in region R1 that uses Ilimbasu 0 as their waste disposal method. After feature engineering, we go down to dimensionality reduction. We choose to experiment on 5 different reduction approaches, and we also preserve the unreduced dataset head as a 6th dataset. The 5 approaches employed are PCA, univariate feature selection, drop high correlations, L1-based feature selection, and tree-based feature selection. The parameters used in each method is shown on the screen. And then we use light GBM and cross-validation, CV for short, to find the best dimensionality reduction approach. Light GBM is a lightweight yet decent model, which makes it suitable for comparison experiments. We use 5 folds to train and evaluate. After evaluation, we found that head only and LSVC FE2 works the best. So we only experimented on these 2 reduced set of features in the next experiments. And now I will pass on to Jingtan to talk about the models.
Thank you, Xinyang, for introducing the feature engineering. Now I will illustrate how we construct our model. We are using ensemble learning, which improves model performance in terms of accuracy by aggregating the predictions of multiple models. It is a trick to win Kaggle computation. The overall structure is shown here, where we are using 3 frameworks, and for each framework we are using various base classifiers, and then we aggregate the results from each classifier for the final prediction. Each framework is also ensemble learning. We are adopting the 2 tricks in the ensemble learning. One is boosting. It iteratively adjusts the observation's weight depending on the previous classification, and bagging. It uses combinations with repetitions to create multi-size of original data. XGB boost and light GBM are boosting, while random forest is bagging. Firstly, we'll zoom in light GBM and XGB boost because both of them are based on gradient boosting. Gradient boost is a statewide additive model, and each base classifier is decision trees. One thing to note that it's used differentiable loss function for functional gradient descent. Due to the introduction of this loss function, it generalized the use cases so that it can not only be used on binary classification, but also regression and multi-class classification, which is our case. Although light GBM and XGB boost are based on gradient boosting, they share differences. XGB boost grow tree depth-wise, while light GBM grow tree leaf-wise, and XGB boost build tree based on exact greedy or approximate algorithm. Light it goes over all the potential divides for each features to build a tree, while light GBM introduces GOSS and EFB, which either reduce the number of data it need to traverse to compute information gain, or it reduce the number or the dimensionality of the features to reduce the time to build a tree. So light GBM is much faster than XGB boost. For random forest, it is actually an extension of bagging. It generates a large number of trees, each of which is based on a random subset of features. Then, the majority vote is adopted to get the final results. Besides the model structure, we also use 3 tricks to improve the performance. Firstly is the RFE, recursive feature elimination. If the data passed to us is still full dimensions, we'll adopt RFE. It is a wrapper-type feature selection algorithm. That is, it uses a machine learning algorithm to eliminate a useless feature after each round. It will repeat the process until a specified number of features remain. Second trick is randomized search cross-validation. That is, we search the hyperparameter space for the best hyperparameter setting. We are using randomized CV instead of grid CV because of 2 reasons. Firstly, the number of parameters and possible values has no impact on the budget. Additionally, adding parameters that does not influence the performance does not decrease the efficiency. Third trick we are using is to manage the imbalance. This was accomplished by assigning the majority and the minority classes different weights. And the goal was to punish the minority classes more for misclassification by giving them a greater class weight, while giving the majority classes a lower weight. The overall pipeline is shown here. firstly data preprocess, feature engineer, dimensionality reduction. Then we use the cross-validation to select the optimal dimensionality reduction method. After that, if we found previous steps still give us the full dimensions data, we'll use RFE to reduce the dimension again, and then pass in various base classifiers, and then aggregate each result from base classifiers for the final result. For the test, it's almost the same process, except that we'll first filter the family head and only use the family head to predict the whole family's poverty level, because the family head actually decides the whole family's poverty level. Then I will pass it to Lily to talk about the results of experimentation.
Thanks, Jingtan, for her clear explanation of how our model looks like. Then I'll introduce the series of experiments that we have done to prove the effectiveness of our solution. The evaluation matrix that used to evaluate the classification result is macro F1 score. It is harmonic mean of the precision and recall, where an F1 score reaches its best value at 1 and worst score at 0. The relative contribution of precision and recall to the F1 score are equal, and the specific equation is shown here. We carried out experiments from 3 aspects. Firstly, we investigated into the head-only feature engineering method. Our default configuration employed 1 voting classifier with 3 base classifiers, without feature elimination. And based on this default configuration, we also evaluated the application of RFE to select the 100 most important features out of 154 features. From the first table, we can see that the score increased a lot from 0.40926 to 0.43497, which means that RFE really helps to simplify the model and enhance the generalization ability of the model. And secondly, based on the head-only with RFE, we conducted multiple experiments on different numbers of base classifiers in the voting assembly. We have set the number at 3, 15, 30, and 45. From the second table, we can observe that when the number of base classifiers increased from 3 to 15, the F1 score increased from 0.43497 to 0.44400. Then the score starts to decreasing and converging to 0.44083. with further increasing of base classifier numbers. As a result, we set the number of base classifiers to 15. And thirdly, we compared 2 different feature engineering methods, head-only and LSVC. For head-only, the RFE was adopted to select the 100 most important features. And for LSVC, the dimension has already been reduced to 37 features after the feature engineering. So there is no need to implement RFE for LSVC. And from the third table, we can see that head-only with RFE works better than LSVC in this situation. So after these experiments, we observed that head-only feature engineering methods with RFE to remove unimportant features and setting the number of base classifiers of each framework to be 5 had the most outstanding performance on the test dataset. And the public and private scores are both 0.44400, and the position of the score is 18 out of 617 on the private leaderboard and 19 out of 617 on the public leaderboard, which all reaches the top 300%. Next, we'll move to the discussion part. First is about the performance of different feature dimensionality reduction methods. From table 4 on the left side, we can observe that data without dimensionality reduction performed the best in cross-validation. This is understandable as techniques applied in dimensionality reduction, like principal component analysis, are aimed to preserve as much information as possible. They serve to speed up the training process of models, and they may boost the accuracy when dimensionality is not too high, but at the same time, remove useful features. As we have a relatively small training dataset, it is possible that these dimensionality reduction techniques in table 4 were swayed to believe that some of the features are correlated or that they contribute little to the prediction, when they in fact are not correlated and play a part in the prediction. From table 5, however, we observe that RFE boosts the accuracy of models significantly. After analyzing the characteristics of the techniques, we realize that model-specific dimensionality reduction methods like RFE may be more accurate than model-agnostic methods in table 4. Then, we'll compare the performance of different designs of model. From table below, we can see RFE really helps to enhance the generalization ability of the model by reducing the unimportant features when using head-only feature engineering method. We also found that the number of base classifiers exceeded an optimal number. The F1 score will start decreasing and converging because the base classifiers in one bag become more correlated with each other. And moreover, we can conclude that head-only with RFE works better than the LSVC feature engineering method in this test dataset. That's all for our group's presentation.